Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. And in this video, we're going to be looking at Chapter 2, and we are going to be looking at the ideal gas law, but we're going to start by picking up one small topic out of Chapter 3, which is the phase rule. Now, we're going to come back to this one again later, but I think that this sort of helps fix in our minds a little bit about what we can look up and how many pieces of information we need. So the phase rule uses pi to represent the number of phases, so solids, liquids, gases, okay? N is the number of components, and R is the number of independent reactions. Now, for our purposes at this stage, there are no reactions because we're only dealing with pure substances. So R is going to be always 0 in this course. N is the number of components, and right now we're considering only pure substances, so that will be 1. Pi, the number of phases, well, gases always mix, and no matter how many gases you have, that will be 1 gas. Liquids, probably it's 1, but we've all made like oil and vinegar salad dressing. You can, in certain cases, have 2 different liquid phases, but for pure substances, that will be 1. And for solids, well, okay, solids are complex. We can end up with a lot of different solid phases. But Gibbs phase rule, and this is derivable, and we'll look at it later, it says that the number of degrees of freedom in a system is 2 minus the number of phases plus the number of components minus the number of independent reactions. Now, degrees of freedom may not sound like anything important to you, but what it tells us is how many independent variables do I need to have to identify the intensive state of a system, right? So did I only need to tell you the volume, or did I need to tell you volume and temperature, right? Or was temperature and pressure enough, etc.? If we look at using the phase rule for pure substances, then, well, first of all, there is only one component, so N is equal to 1 for a pure component or a pure substance. And R, we've said, is going to be 0. Well, first of all, pure substances are unlikely to react with themselves. Not that they can't, but they're unlikely to. And so therefore, my formula simplifies down to F is 2 minus pi plus 1, or 3 minus pi. So if I have a single phase system, like all gas or all liquid, all solid, pi is equal to 1, and the number of degrees of freedom is 3 minus 1, or 2. So telling me 2 things is enough to tell me what the phase of the system is when it's only one phase. If there are 2 phases, so a solid liquid at equilibrium, so one of those boiling mixtures, pi is equal to 2, and the degrees of freedom, therefore, is 1. If I know that it's a 2-phase mixture and I tell you the temperature or the pressure or the volume or whatever, then that's enough to tell you what the state is. For a 3-phase system, I have 3 phases in equilibrium at the same time. Degrees of freedom is 0. And what this tells me is that I have something that nature gets to determine what the temperature and pressure will be. I don't get to choose, nature chooses. Another kind of topic that we want to talk about is ideal gases and the ideal gas state. Now, you've had a chemistry course, so you've talked about ideal gases before. Ideal gases don't exist. Okay, so let's get that one out of the way. But we can say that something behaves like an ideal gas if it meets these 4 conditions. And the first one is it has to be a gas. If it is a liquid, it is not an ideal gas, okay? But next, I need to have molecules that are small and spherical. So they need to be round. They also need to be very small. They need to have essentially no volume. The molecules also need to be far apart. That happens when you have a low pressure state. The molecules are spaced well across the room, the container that it's in. And so this tends to go with low pressure. This is very small volume of the molecule. And then finally, that the molecules have no attraction or repulsion. So polar chemicals are going to have a harder time becoming ideal gas-like than others. Now again, nothing is truly an ideal gas, but they can be ideal gas-like. And if it is an ideal gas, then we have the ideal gas equation of state. And we've used this before, probably not in exactly this form. Now, we are going to use R, sadly, not as the universal gas constant sometimes. We're sometimes going to use it with mass. Now, we know the universal gas constant is 8.3145 kilojoules per kilomole Kelvin, or kilonewtons times meters per kilomole Kelvin. I enjoy working with mass units sometimes. Take your universal gas constant and divide by the molecular weight of the substance, and that gets you a value for R that is unique for that compound because it's dependent on the molecular weight. Now, I'm not going to write it any differently when I do that. You just need to know that the molecular weight is going to be how you fix your units using this. So instead of PV equals nRT, what you used in chemistry, PV equals mRT using this unique gas constant, not the universal value. And I can divide both sides by m and get this into a specific form. If I do divide by the number of moles, this is the universal gas constant and this is the molar volume. P times the molar volume is the universal gas constant times T. Now, key things for you to know. The pressure and temperature absolutely must be absolute. So temperatures need to be in Kelvin or Rankine. Pressure needs to be absolute. You've added the atmospheric pressure to it. In this course, P is going to be absolute unless we state explicitly otherwise. Okay? Temperature you'll know by the units. Pressure for this course, assume that it is absolute. Now the units for V are going to depend on the units of R. It's either molar volume or specific volume, depending on whether you use the universal gas constant or the specific one for your compound. Whichever you do, if you have a closed system, then the mass or number of moles remains constant, and R is always constant. And so therefore we can say that P1V1 over T1 is equal to P2V2 over T2. And there are all sorts of variations on this rule, like if it's a constant volume process or something like that. But really, I find this version is the most helpful. And it's just the ideal gas law rearranged for constant mass. If we wanted to look at how we might use this, combining this with our knowledge of tables, if we looked at water at 800 degrees C and 2 bar, and know that it has a measured specific volume of 2.475 meters cubed per kilogram, we want to know whether or not we can consider this an ideal gas. So the trick is, let's just estimate then, using the ideal gas law, let's estimate the volume. So you might pause the video and work this on your own. If we evaluate the volume using the ideal gas law, RT over P. They have given us an R value for mass units for this material, water, 0.4615 kilojoules per kilogram Kelvin. I'm going to multiply by the temperature, but it's in degrees C, so I will add 273.15 to convert that to Kelvin. And the pressure is assumed to be absolute. Kelvins cancel, bars don't quite cancel, but 1 bar is 100 kilopascals. And a kilopascal times a cubic meter is 1 kilojoule. So kilojoules cancel, kilopascals cancel, bars cancel. I'm left with meters cubed per kilogram. V for the ideal gas calculation is 2.47476 meters cubed per kilogram. All right, this is very, very close to being an ideal gas, right? It varies in the 4th place. One way that we can quantify this is people look at something called Z, which is the compressibility factor. And Z is defined to be the volume we actually have divided by the volume we would have if it were an ideal gas. And in this case, 2.475 over 2.476 is equal to 0.9996. What we usually are looking for is for Z to be very close to 1. How close? Well, it depends on what we're trying to do. But normally I work with in 2%. So 0.98 to 1.02. In this case, it's very close to 1. And so therefore, this is an ideal gas. Okay, here's another one. 250 degrees C and 20 bar. I can again do the calculation. You should pause the video and do this independently. R is 0.4615. Temperature is 250 plus 273 Kelvin. And the pressure is 20 bar. I multiplied by 100, and that puts the units as kilojoules per cubic meter. That's trying to shortcut all those conversion factors I did a moment ago. And so we get 0.1207 meters cubed per kilogram. Z, therefore, is 0.0871. The actual divided by the ideal gas, 0.7217. So therefore, this one is not an ideal gas. If I know the substance is a gas, this actually can work for liquids too, but not quite as simply as what I'm laying out here. But I can write an equation that will allow me to do calculations directly without having to look things up in tables. But I need to know, for instance, is it an ideal gas? If it is an ideal gas, then I can relate pressure, temperature, and molar volume using the ideal gas law, right? So PV equals RT, and that would be for molar volume. Or I could say that pressure is RT over that molar volume, right? This is called an equation of state. It relates pressure, temperature, and volume. But what if the gas is not an ideal gas? Well, I have several other choices, but we'll look at two. One of these is the van der Waals equation. It is the first good equation of state that was developed historically. And what it does is it has a correction, V minus B in the denominator, to correct for the fact that molecules really do have size, right? One of our assumptions was that molecules were round and had no size. So the B in the van der Waals equation accounts for the fact that they do have size. And then A over V squared accounts for the fact that they are going to have some attraction to each other in some way, okay? So that attraction repulsion thing is going to figure into this A over V squared. And the A and the B are going to be dependent on what type of compound you're looking at, right? They are things that you can look up. Another equation of state we have is a compressibility factor equation of state. And all that does is it says that, remember Z is the compressibility factor is V over V for the ideal gas. And I could do this with molar or specific. I can use that, therefore, to say that pressure is Z times RT over the volume, the actual volume, right? VIG is going to be RT over P. And so therefore, I can solve for P and get this expression. So these are going to be ways that I can have an equation. Now, I would need to know what Z was in the compressibility factor equation. I would need to know A and B in the van der Waals equation. Let's just very briefly look at an example where we're using the van der Waals equation. So for water, the van der Waals constants are A is 0.5542 Pascal cubic meters to the fifth per mole squared, and B is 3.051 times 10 to the minus fourth meters cubed per mole. And we want to be able to calculate the specific volume of water at 8 bar and 350 degrees C, and then we'll compare it to what we get in the steam tables. Now, first of all, this pressure is in pascals, not kilopascals. So if we have 8 bar is 800,000 pascals. Okay. And this is going to be RT, so 8.314, full version 447, meters cubed Pascal per mole Kelvin. That's R. T is 350 plus 273, or 623 Kelvin, divided by V minus B, 3.051 times 10 to the minus fourth. That's going to give me meters cubed per mole, minus 0.5542 Pascal meter to the fifth per mole squared, all over V squared. Okay. Now this turns out that if you try and clear to fractions, it's a cubic equation of state, third order polynomial. I solved this with Excel. You can solve it whatever way you choose to. I got that V is 0.067 cubic meters per mole. Now, to be able to compare this to the table, I need to work with this in mass units. So 18 grams per mole is the molecular weight, 0.000371 meters cubed per gram. Our table is in per kilogram, so multiply by 1,000, 0.371 meters cubed per kilogram. Now then, what if I use the steam tables? In the tables, if you look this one up, you get that the volume is 0.354 meters cubed per kilogram. This gives me a percent error of 0.371 minus 0.354 divided by the correct one. Now, which one is correct? The tables are the correct one. Any equation is only going to be an approximation. So dividing by the correct one, 0.354, this gives me 0.049 or 4.9% error. In other words, it does a pretty decent job. If I want to minimize my error, improve my precision, I'm going to use data tables. But equations can get me within, in this case, 5% of the actual value. Now that concludes this video lesson. When we come back, we're going to continue looking at Chapter 2, but we're going to look at other things we can do with these properties. Thank you very much for your time. So this concludes this video. We want to come back and look at specific heats or heat capacities and how they relate to properties in our next video. Thank you very much for your time.